Axial or longitudinal stress. So axial stress is a stress that occurs in a pipe in longitudinal direction. It is caused by internal pressure acting on the end of the pipe. To calculate the longitudinal stress, we can start from the stress formula sigma L is equal to F over A. Means the applied internal pressure force inside the pipe is equal to the resistive force of the pipe material. When the system will be in equilibrium, the applied internal force inside the pipe is equal to the resistive force of the pipe material. Consider a pipe having a length L, thickness T, inside diameter di. When the internal pressure is applied to a pipe, the pipe will try to expand in longitudinal direction. The area that will fail due to longitudinal stress is the ring-shaped area of the pipe, which is highlighted in yellow color. This area will be experiencing the stress that will try to elongate the pipe. Now, the force that is creating the stress is internal pressure, which is equal to the force divided by internal area. So the force is equal to the internal pressure into internal area of the pipe. In this case, the pressure is equal to P internal pressure, area is equal to pi by 4 d square, which is projected area where the internal pressure is acting. Therefore, the applied force is equal to P into pi by 4 di square. Now calculate the pipe resistive force on the right side against the applied force. So the longitudinal stress is equal to force divided by cross-section area of the pipe, and the force will be equal to the longitudinal stress multiplied by the cross-section area of the pipe. Now the cross-section area of the pipe is pi by 4 into dO square minus di square as the area of resistance. Now substitute these two values, the applied force and resistive force, in equilibrium equations. So we'll get P into pi by 4 di square is equal to sigma A pi by 4 dO square minus di square. So from here we can simply cross the pi by 4 from each side of the equation. Then P into internal diameter is equal to sigma A dO square minus di square. Here, to calculate the sigma A, we can say that sigma A is equal to, which is axial stress or longitudinal stress, P di square over dO square minus di square. As we know that dO square minus di square is equal to dO plus di into dO minus di. This is the basic formula in mathematics. Whenever we have square of two things, it will be equal to the product of the plus and minus. Here let's consider these dO plus di and dO minus di separately. So dO minus di is equal to 2t, which is the thickness of the pipe, as we know that. So we can say that dO plus di divided by 2 is equal to the mean diameter of the pipe. From this mean diameter of the pipe, we can say simply dO plus di is equal to 2 dm. So let's substitute these values in the equation and we'll get the sigma A is equal to P di square divided by 2 dm into 2t, which is equal to P di square divided by 4 dm into t. dm, which is mean diameter, is always greater than the inside diameter of the pipe. Hence the calculated stress from mean diameter in denominator shall be less than the calculated stress through inside diameter in denominator. Hence the inside diameter gives more stress values, which is again conservative approach. Now cancel the di with di square and we shall get the final formula of longitudinal stress, which is sigma A P di over 4t. But in actual calculation we use outside diameter of the pipe, which is again greater than the inside diameter of the pipe and gives us more stress value. So another conservative approach. So it means sigma A is equal to P d O over 4t, where sigma A is the longitudinal stress, P is the internal pressure, D is the outside diameter of the pipe, and T is the thickness of the pipe wall. Sigma A is equal to PD over 4T is the formula to calculate the axial stress. So axial stiffness of the pipe is normally calculated through E into A divided by L. Bending stress. Let's try to understand the concept of bending stress and how to calculate the bending stress in a pipe. The bending stress is a difficult concept, and I'll try to simplify this concept so that you can understand easily. So bending stress, which is sigma B, is equal to M over I multiplied by Y for transverse or lateral loading, where M is the bending moment, I is the area moment of inertia of cross section about the axis lying x-axis or y-axis, means it is the resistance property of the cross sectional area. If the length of the pipe is subjected to a constant bending moment and no shear force, means shear force is equal to 0, then the stress will be set up in the length of the pipe due to bending moment only. Then it is called the pure bending moment. And the formula that you can see here, sigma B is equal to M over I into Y, or SB is equal to M over I dot Y, or SB is equal to M over Z. It is extracted from this formula M over I is equal to sigma over Y is equal to E over R. Let's calculate how we have derived this formula. When load acting in a plane normal to the axis of the pipe, the bending stresses are developed in a pipe, and due to the load or force, the bending moment acting in the plane of the pipe is called in-plane bending moment, and stresses developed due to this bending moment is called in-plane bending stress, which is SB. Similarly, bending moment acting perpendicular to the plane of the pipe is called out of the plane bending moment, and the stresses developed to this moment is called the outside or out of plane bending stress. Under bending, top fiber of the pipe subjected to compressive stress and bottom fibers are subjected to tensile stress, while the middle layer neutral axis there will be no stress due to the external load or force. Let's prove mathematically how we can calculate the bending stress through the equation, which is M over I is equal to sigma over Y is equal to E over R, where sigma is the bending stress, M is the bending moment due to resistance, I is the moment of inertia about neutral axis, E is the Young modulus, R is the radius of curvature of the neutral axis, Y is the distance from the neutral axis to the extreme fiber of the cross section, as you can see in the picture. So SB is equal to M over Z, where Z is the section modulus of the pipe. To calculate the bending stress, we need to assume few conditions. The first condition that we need to assume, the pipe will experience pure bending, means the shear force is equal to 0, torsional force is equal to 0, axial force is equal to 0. In practical cases, it has been observed that the bending moment is maximum where the shear force is equal to 0. Second assumption is the pipe material obeys Hooke's law, means we shall consider load and deformation within elastic region of the material. As we know that sigma is equal to E into epsilon, which is equation 1, as you can see right now. So epsilon is the ratio of change in length to the original length. Let's consider the straight strip RS and PQ on the surface of the pipe. The PQ is on the neutral axis of the pipe, and RS, the strip RS, is at a distance y from the neutral axis of the pipe. As you can see in the picture, I am indicating through my cursor. So when no loading, then RS is equal to PQ. During loading, there will be no stress at neutral axis, hence the strain induced at neutral axis is zero. Mean when there will be a bending moment, or the pipe will be in bending condition, the stresses at the neutral axis, it will be zero. It means the strain at the neutral axis, it will be zero. So when no loading, so RS is equal to PQ. This RS, which is the strip at a distance y from the neutral axis, it is equal to PQ. Now after loading, let's apply the loading, and when the pipe will be in bending condition, so the top fiber of the pipe will be under compression and bottom fiber of the pipe will be under tension. So at this location we'll get the tensile stresses, and at this location we'll get the compressive stresses. But the neutral axis, there will be, or axis of the pipe, there will be no stress. So now after bending, P into Q is equal to P prime into Q prime, which is equal to R into alpha. Means PQ, which is at the neutral axis, it will remain same, P prime and Q prime. And if you calculate this P prime Q prime, it will be equal to R into the angle alpha after loading. Similarly, R prime and S prime, R prime S prime is equal to R minus Y, this distance, which is from the neutral axis. The distance of this strip R prime S prime from the neutral axis, R minus Y into the angle. Now the strain in the layer RS due to the bending, it will be strain is equal to R into alpha minus R minus Y into alpha divided by R into alpha. This is the original length, this is change in length. So change in length divided by original length, if we'll simplify this, we'll get Y over R. Hence the strain shall be E is equal to Y over R. Now put it in equation number 1 here. So what we'll get, sigma over E is equal to Y over R. Or we can write it like this, sigma over Y is equal to E over R. Or we can say that sigma is equal to E over R into Y, which is equation here. So sigma over Y is equal to E over R is our final product from this calculation. Now we will calculate the second part of the bending stress. So now let's calculate the bending stress in terms of bending moment in a pipe. Consider again the small strip of area dA. As you can see here, small strip of area dA, which is very small area, okay, at a distance y from the neutral axis again. So as we know, the normal force on this area is equal to the stress into area, which is sigma into dA, where dA is very small area of the strip. Normal force is equal to stress into area, which is F is equal to sigma into dA. As we know that the stress that we calculated in the previous page or previous slide, E over R into Y multiplied by dA. As we know that sigma is equal to E over R that we calculated in the previous slide, the moment is equal to force into distance. So this force that we calculated now, if you multiplied with this distance y, we'll get the moment, which is M is equal to E over R into Y multiplied by area, small area dA multiplied with distance y. So this way we'll get the moment. As we know that I, which is moment of inertia of the pipe, is equal to the area multiplied 2 times by with the distance or square of the distance. This is equal to the moment of inertia of the pipe. So we can say that M is equal to E over R into Y square into dA is equal to E over R into I. So from there we can simply calculate that the bending stress is equal to M is equal to E over R into I, or M over I is equal to E over R. Here we know that the bending equation, which is sigma over Y is equal to E over R is equal to M over I, where I already told you is the moment of inertia of the pipe, and this moment of inertia of the pipe is I is equal to pi by 64 outer diameter raised to power 4 minus internal diameter of the pipe raised to power 4. This is the moment of inertia of the pipe. So the SB is equal to M over I into Y, which is equal to M over I over Y. We can write it like this as well, right? So I over Y is equal to the section modulus, as we know. So SB is equal to M over Z. So we have proven all these equations. Sigma B, which is bending stress, is equal to M over I into Y, or SB is equal to MI over Y, or SB is equal to M over Z, or M over I is equal to sigma over Y, which is equal to U over R. So we have calculated all these values. So bending stiffness is equal to EI over L cube. This is additional information for you. So we can say that the section modulus of the pipe strength depends mainly on the section modulus of the pipe.